So with that, we'll move to a different problem, and that is essentially reversing ozonolysis, forming an alkene from a carbonyl group. It looks like this. It has to be an aldehyde or a ketone. We're going to use a relatively odd phosphorus species. Generally has 3 aromatic rings on it, so I'm not attempting to draw it geometrically correct because I want you to see the intermediate step. And we're going to have a negatively charged carbon, like so. This is called an ylide. It has a resonance form because you can go beyond the octet rule for phosphorus, but it's easier to draw what's happening from here. Okay. Who's attracted to who here? What? Yes. This is our active nucleophile. A negatively charged carbon is generally really interested in being something else. So it's going to be a strong nucleophile just like everything else we've seen. Now, that's going to cause us some stress. This is called a beta-ene intermediate. Betaine, I'm not sure how it's actually pronounced. I've heard it's pronounced both ways by former professors, but neither of them was particularly well spoken, so I'm not sure what the correct pronunciation is. One of them I'm pretty sure was English as like a 4th language, so I don't know that his pronunciation would be ideal. He serves as a negative role model for my life, so that's what I learned from my organic professors. What not to be in life. Okay. He's the one who came in the first day of organic and gave the speech, which you've all heard about, but hopefully didn't hear, which is look to your left, look to your right, one of those people is going to fail. And maybe both. That was the old speech. I don't do things that way. All right, 4-membered ring, ugly. This is an oxyphosphatane. We've dealt with 4-membered rings. They're not completely unreasonable. We can have them. But is this ideal? This is in fact a loaded question. It's loaded by the fact that one of the worst things you can do in the world in trying to understand reactions is abbreviate things. Here, let me try it without the abbreviation. exactly the world's greatest drawing, but you get the point, right? Does this look like a reasonably stable, happy camper type structure to you? Absolutely not. That phosphorus is a behemoth with 3 aryl groups attached to it. It is massive. So, what happened? Partially correct. Partially correct. You would be left with a carbon attached to oxygen and nothing attached on the other carbon. How about this? That type of thing look familiar? Like something maybe we saw before? 4-membered ring electrocyclic opening? Or electrocyclic ring opening, yes, that's the word. I thought I had said electrocyclization, so that wouldn't be a cyclization. It's an uncyclization. What happens? We end up here with a double bond. And we end up with, I'll go back to the abbreviated form for the moment, triphenylphosphine oxide. Ah, nice. Except for, well, how do I make this stuff? Ooh. I did sort of warn you that question was going to come up a lot, right? You're going to have to tell me how to make things often. And we're going to add even more complexity to it because we're going to play the stereochemistry game. Where did that magical phosphorus with a carbon anion nucleophile come from? Generally, the easy method, triphenylphosphine, cheap, readily available, somewhat toxic, not the kind of stuff you want to wash your hair with, but still not difficult to handle in the right setting. And an alkyl halide. What do you think is going to happen here? SN2 reaction. Okay. So now I have a phosphonium salt. And I have no nucleophile. How am I going to get a nucleophile out of this? That would be an enormously unfavorable acid-base reaction. HI is exceptionally strong as an acid. That is a terrible base. In actual fact, I have to add something to it. Generally speaking, I add a very strong base. Typically something like butyl lithium, or sodium hydride, something along that nature. Very, very aggressive bases. And what they will do is tear one of those off. So, to draw that properly so we can see it, now I have my active nucleophile. I just ripped a hydrogen off of a methyl group. Methane's pKa is 60. How am I going to do that? Butyl lithium ain't going to take a hydrogen off methane. Why is it going to be able to pull off that hydrogen? Why is that hydrogen acidic in the first place? Not likely. And you're thinking product-wise. I'm asking you reaction-wise. Why would that reaction start, not why would it finish? You may be right about the stability, but that's not why it would start. No. No. What's a positive charge doing to the things next to it? Drawing electrons away. That carbon is not partially negatively charged. That carbon is partially positively charged because it's losing electron density by sitting next to a cation. As a result, so is the hydrogen. Hydrogen that's losing electron density is more acidic. That's the very definition of it. The more electron density you take away, the closer you get to H+. So, that's why. Okay. So here's our active nucleophile. We have to use a solvent that tolerates that. Usually we're talking about an ether solvent, something like THF. That's very common as a solvent for butyl lithium. You could use diethyl ether. You could use dimethyl ethylene glycol, or ethylene glycol dimethyl ether. There's a lot of different possible ether solvents, basically polar, aprotic, but without any CO double bonds or SO double bonds from the SN2 type solvents you learned back in the day. This is an SN2 reaction. So, what's my limitation? What can't I do? Tertiary. Is that a big limitation here? Why not? You don't even have to look at the upper board. Look at the bottom one. I need at least one hydrogen there to do anything with it. Otherwise, I don't have a nucleophile. So I couldn't have used the tertiary anyway. It can only be secondary or less. Otherwise, I have no way to make a nucleophile out of it. And I'm just playing with phosphorus. Okay. Now, this is called the Wittig reaction, spelled Wittig for George Wittig, who designed it, came up with the idea. It is by far the most common alkene synthesis that you'll see in the literature because it works very easily, generally very well, and does not require any of the true nastiness that you saw back in the E1, E2 type chapters where you could get multiple different alkenes and possible cation rearrangements and things like that. None of that is possible here. This reaction will give a single product every single time. Sort of. Okay, so let's deal with practical examples. Big advantage if we need what is called an exo double bond. So if I want something like this, where I have a double bond attached to a ring directly, that is almost impossible to do with an elimination. No matter how you arrange things, it's almost impossible to do with a standard E2 or E1. Very, very difficult. With this, simple. Cyclohexanone. And the exact nucleophile we just made. Done. No other possible alkene. No worries about stability. So you can make exo double bonds using this very easily. The problem is going to happen here. This doesn't have to be aromatic, but it's an example where I have the numbers, so I'm going to use it. If I have this, now what? My product is going to be an alkene with an aromatic ring on each end. It's called stilbene. But what's the problem? Yes. I have one substituent on each carbon of an alkene. What does that mean? What does that produce potentially? Stereoisomers. Cis versus trans. Ooh. Let's actually look at the numbers because I don't remember them. Okay, so this exact example reaction works relatively cleanly, and works reasonably favorably towards one stereoisomer. The standard Wittig conditions tend to favor the Z alkene when stereoisomerism is possible. Well, as I'm sure you've gotten the impression from watching me for the past 2 or 3 weeks, organic chemists tend to be like spoiled children. That is, no matter what we get, we wanted the other one. But I wanted the other dolly. I wanted the other game. I wanted the other toy. Why'd you buy this one? Go get the other one too. We don't want them together. We don't want mixtures. But occasionally, we may need the other stereoisomer. There are 2 ways to go about that. One, we can basically isomerize this because trans will be easier and more stable eventually. That's kind of painful and potentially risky. Or we have to modify the phosphorus, which is in fact much easier to do. This is a variation called the Horner-Emmons reaction. Rather than using triphenylphosphine, this is the Wittig, we're going to use basically an alkyl version of a phosphonic acid. So we're still going to have the same type of nucleophile, only our phosphorus structure is going to be very different. The Wittig tends to favor the alkenes. Horner-Emmons conditions tend to favor the E. So in this exact example, we end up with, they didn't say whether this is yield or whether this is ratio, so I don't know the answer to that, but it's interesting either way. 63% of the E isomer. Completely different preference from the standard Wittig conditions. So with choice of phosphorus reagents, I can control stereochemistry of alkene formation. I do not intend to make this into a huge, huge topic. Quite honestly, if I wanted to, I could teach an entire course on this reaction. It's that large of a body of literature with different phosphorus reagents and different chelating agents and different this and different that. I don't need that much detail. But I do want you to know that one has a preference and you can change it by altering the sterics and the electronics of the phosphorus. This is as far as I'm going to go with it. I don't think your book even goes to the phosphonate. But the idea is that there is a stereochemical preference. Because we're going to talk about stereochemistry in a lot of other contexts later in the course, we still have to keep it in our brain. So when a reaction has a preference for one stereoisomer out of a mixture, we need to think about that. And also think, well, if it has a preference, how would I screw it up? How do I make it do something else? Well, you don't have any real choice in the nucleophile. It has to be the alkyl group. You don't have any choice in the electrophile. That's your carbonyl group. So you've got solvent, and you've got the phosphorus, and that's really all you have to play with. So that's how it works. You can see it's not 100% either way. It's not perfect in either case. You could tweak it. You could add bigger groups here, or have a sulfur here, or you could have, much, much bigger aromatic rings on triphenylphosphine. You can tweak it, but those have never proven to be overly practical. And from what I've read, they don't tend to make giant jumps either. Like you might be able to take that 70 up to about 80, but you're not getting it up to 95. There's just no way to have that much of a preference. Not without engineering a scaffold that would be 10 times more work than just making a new alkene.